Week 7, Lecture B. So today we are going to do MIMO. We're going to do a MIMO realization. So Monday we basically did SISO. Okay. So it is minimum. It is always minimum if you don't have a post-zero cancellation. If and only if actually, no post-zero cancellation. Okay. If you have a cancellation, then it's a problem. So you may wonder something called stabilizability. Okay, stabilizability. There's a concept is called stabilizability. Some of the system is fundamentally not stabilizable. In other words, you have a subspace that is not controllable, okay? Not controllable, and it is not stable, okay? So I'll give you one simple example here. So you have S plus 1, you have S plus 1, S plus 2. So when you do this, if you do a second order AX dot is AX plus BU realization, if you A is 2 by 2, then this realization will be controllable, could be unobservable, okay? Could be, so we have seen this example. But did you ask yourself that, what if you have something here? Okay? You have an unstable pole cancellation, okay? So although you still can talk about realizability or controllability, but because you canceled out something unstable, okay? Although you can cancel it, but this system is already not stabilizable. Okay, it's not stabilizable because there's something beyond your control, which is unstable, by the way. Okay, so just be careful for the SISO case. We haven't talked about this one. We talk about plus, okay? So here, that's a concept. Later on, we are going to, when we learn stability concept, we are going to come back and visit this again. So here is what we have. Yes, here is another thing I need to tell you about our plan. Okay, here's our exam plan. Exam plan. So first of all, if you want to get a good grades, you cannot do a very bad job in your homework. Because homework is 50%, okay? So it's a training, and it doesn't matter you get help from me, from classmates, it's okay. Please interact, have group study, and have group. Basically, it's a group study when we do every Monday. So I suggest you guys organize a group study between yourself. So exam plan, midterm. I want to do in the week 9. Week 10 is Screenberg. I'll leave you guys alone. So week 10, nothing, okay? I thought about this. So then I do final exam. Final exam will be also in the week 16. So you can focus on other things. And all these will be in class, 90 minutes. Okay, in class 90 minutes. So the questions will be selected from your homework or from those typical ones. Okay? So, most of them is tested your concept. Okay? So I'm going to give you the problem set way ahead of time. So let's recall what we learned last time. For input-output concept of realization, we covered about general LTV case. Remember, I think we have that one. It's a GT comma sigma. Okay? So time varying realization, talking about minimum realization without pole zero cancellation is a minimum realization. Okay, it's a minimum realization. So then we also learned controllable canonic form, controllable standard form, or whatever, observable form. Okay, so and pole zero cancellation. If you don't have it, that's already minimum realization. We talked about it. And I think we had something original and creative on last lecture. What's that part? I indicated that in the state space realization, in the state space description, it is a realization based on 3 building blocks: summation, gain, and integration. Okay, integrated. And using op-amp, you can see op-amp using the SISO realization. You understand how to define x1 and your xn, the internal states for transfer function GOS, which is A of S, B of S, polynomial. Okay. So we have learned those tricks. And also, by the way, we learned all this standard form. And this is SISO. You have ratio polynomials, strictly proper. So you know these things. And the D, in this case, direct transmission term. D is called D is 0 when the degree of B greater than degree of A. So this is strictly proper. Okay? And this is called direct transmission term. And this one is directly goes U to Y without going to intermediate step. So this is go to this D. Okay, this D. And in most of the engineering system, we don't have this D. D is 0 for like 99.99 case, as I have seen so far. Okay, so majority, most systems is strictly proper. There is another word. It's called real. Strictly proper real. It's called SPR. So it's called strictly proper realness. I like it. Realness. That's in robotics control. There are a lot of such kind of concepts. So we have learned this before. So ABCD is realization. So that's something I hated here. I don't like the word the realization. I don't like that. But in this context, it's still correct to use the because realize G bar, this is strictly proper to get, this is one of the infinite many realizations. So this is a realization. But when you plug in the D back, so is the realization. I think it still says a realization of the original G. Okay. Yeah, their realization, I don't like it. Probably it's a typo. Should use is zero realization based on this plus this. Yeah, that the sense that is correct. Okay, is the realization derived from that for the G of S. So, make sense? So this is the polynomial, right? And this is the monic, because the highest term in the denominator is 1. And then you can write the polynomial. Because of the polynomial, you write this form. Okay. I don't want you to confuse this one with the model controllability matrix. So in that case, you have to talk about a Jordan block, right? Diagonal, block diagonal case. Then you check which B is non-zero, okay? Or we have learned that kind of thing before. If it's all the diagonal, then you check the B. Then if B is not zero, then it's controllable. But in this case, it's a canonic form, controllable canonic realization. So in other words, you just have a cascaded integrators. Okay, remember? Cascaded integrators. Even in, so then this one is observable canonic form. So again, I want to remind you, this is like the previous B transpose. This is B is C transpose, previous C transpose. And this one is A matrix, okay? A matrix. That is also transpose and negative. Basis change will not change observability or observability. So we are going to check a few examples here. Okay. First of all, you have A, B, C. This is LTI. So I want to understand what is this minimum? Is this minimum realization? That means is this both controllable and observable, right? So then I want to find a realization in standard controllable form. This is obviously not, okay? So this is, we need to find a way to do it. So this is a requirement. Anything on this example that can be computed without a computer calculator, you should pay a special attention. Those questions is the one we put in the exam. So when we have this one and we check the transfer function, okay, and because there's some tricks in here, because A matrix has some upper triangular form, and here is lower triangular is 0. Therefore, whatever you do in here, because of the structure in here, this is a diagonal. So then you end up with this one as well. So C and B, phi, everything like this one. Although I don't know what's inside, but it doesn't matter. So what I have end up with is phi 1, 2 plus phi 2, 2. By doing this, doing this, so you have, then in the end you have only this term. So I hope you don't want to solve this one first. It's too complicated, 3 by 3. So what we do is 5 to 2, we check about, this is a definition of what? Matrix inverse, okay? So determinant of this thing, determinant of this thing. So then determinant is diagonal, you have this one, 1, 1, 2. So you have a 2. So basically you have an algebraic multiplicity of 3, geometric 2. So adjacent matrix is this one. So basically you cross that 2, 2 term, cross that 2, 2 term, to cross this 2 term is s plus 1 minus 1 and 0 and s plus 2. So you cross this s 2 term, you do this one, you do the determinant is the adjacent of this one. So you end up with this. Okay. And 1, 2 is what do you have? Is 1, 2 is an odd number, so this is negative. Okay. Then you do you cross 1, 2, you cross 1 and 1, 2 is here. Cross this guy, cross this guy. No. 1, 2 is 2, 1. Okay, you cross this one. Okay. Or this one. So you cross this one, you got a -1, -2, 0, and +1. So you end up with this one. Okay. So together, what you end up with, G of S, it will be something like this. Okay. Then you have something called cancellation of 0 and pole. Okay. But both of them are stable poles, right half plane. So left half plane, so -2, left half. So this cancellation will not cause problem, internal stability problem. So that is second order system. Remember, A matrix is 3 by 3. Okay, 3 by 3. So therefore, this is lower than 3, then this is original system realization is not minimum. It's not minimum. There's no cancellation in here, then A matrix must be 2 by 2. Make sense? So from here you are going to see, you write this way, you are going to have a standard controllable realization is A is this, B is this, C is this. So that's simple, we know it. Okay? Then it's controllable canonic realization form. D is 0. Okay? So you still need to get the G of S, okay? But when you do G of S, you really need to make use of the structure of the original A's of the triangle. That will save you a lot of redundant computation. Make sense? Do that way. This is a smart way. Let me go through this one with you one more time. So you have an example like this. When you have seen this A, you pay attention to this structure, okay? Upper triangle. Okay? And you want to make this one minimum, check is minimum or not. It's not a minimum because it's not controllable. It's very easy to check. You can use B, AB, A square B. The rank condition, you can do that. So then we need to get transfer function. This is 3 by 3, and G in the end you are going to see. So we want to minimize the effort to solve this one. Then we make use of the structure in here. Okay. So we actually only need to compute 2 components, 2 out of 9. Okay. 2 out of 9. You can save 7 out of 9. So there's a lot of saving time. So then with this 2, you are going to get this, you are going to get this, and in the end, you get G's put together, and you end up with this. So you get a cancel out in here, this cancel out. Then you write in the polynomial form, this monic polynomial form, then you write standard. Well, today we are going to focus on MIMO. Okay, MIMO is much more complicated, so we should pay attention and please try to focus. So, when I said realization, I didn't say minimum. Okay, so it could be more than minimum. Okay, then how do we squeeze out? Make it minimum, that's the next step. So what we're going to have is P by N. This is called transfer function matrix. So TFM. You heard about somebody called MTF? matrix transfer function, or transfer function matrix. Very different. The reason is transfer function matrix is talking about Gij is a function of S. Okay. G of S. Okay. So this is a transfer function matrix. So finally, it's a matrix. Okay. But what is a matrix transfer function? Matrix transfer function is you have so you have a numerator of S, and you have a denominator of S. So this is a matrix. This is also a matrix. Okay. So NS is sigma like B I equals 0 to M. So this is a polynomial with coefficients as matrices. Okay. So M is M. Okay. So this reminds you. You can say this is also G of S. So this is like P by M, right? P by M. So you can also write. This is a matrix. This is a matrix. So this is P by M. So P times something, N. So there's N times M. Okay. So you always can do this type of polynomial. So these are the polynomials, polynomial matrix, polynomials of S polynomials with matrices as coefficients. Okay. So this is used very often in robust control. Okay, they use this one. Sometimes they call it coprime factorization. So our textbook has some parts on this topic, but this is not used as often as a state space, of course. Other people want to use this one. M inputs, strictly proper, P outputs. So you define a common denominator, okay? Common denominator. So it's possible to have a common denominator, okay? Determinant of G of S is definitely, okay? It's definitely determinant is a function of S, okay? Function of S. So if you put polynomial G of S, so then you will see NG will numerator will be a matrix polynomial. These are polynomials, okay? Polynomials. So this is a scalar polynomial, only a common polynomial. Well, we will see examples next. So usually you write N of S dg of S. So, but it's different to the concept in here. We're not doing this one anymore. So it's different, okay? So there are two types. One is transfer function matrix and matrix transfer function, okay? What is a strictly proper? That means that common denominator's degree is the highest. So it's called ND, okay? Denominator, common denominator. So that's called strictly proper. Or any of these polynomials here, the highest is still less than this. Then we'll call strictly proper. And of course, the reason they mention the common denominator polynomial has highest order here, coefficient 1 is harmonic, okay? Then for each of the polynomial I, J, and you do K, s to the power k, nd minus 1. Why we can do nd minus 1? Because I want to be less than nd. So I can assume it is nd minus 1. What if I don't have so many? Then coefficient is just 0, okay? So that in general, we can write that way. So in other words, we will be able to write n of s in this polynomial of s with coefficients as matrices as coefficients. Okay. Okay. So n is a matrix. Okay. So then, for each of this gamma k, these are the coefficients here. Okay. For each of the given k, our gamma ij will form like that. So these are just notation. When we say 0m is m by m, 0 im is m by m identity matrix. So then how many states we may have? So we have n is nd times m. What is the m? We remember. P by m. Okay? P by m. So m is how many inputs? P is how many outputs? Okay? So nd is the denominator's high degree times how many inputs? M. That is the total number of states, n. Okay? N. So we're talking about MIMO because you have n. Okay, you have n. Sorry, because you have m. You have m inputs. Each input you will have nd. So this starts to look interesting. So m is remember m is number of my inputs. Okay. So we define x like that. Okay. Nd times m. Okay. So how many coefficients here? We have nd coefficients. Okay. So this is nd times m. Okay, nd times m. And here is also nd times m. So nd. So it's nd by nd block by block. So each of them is m by m box. Okay. So matrices. Okay. So in this case, we do the determinant. We're going to have s I minus a determinant will be this polynomial. I think this is clear. Let me go back and show you what's going on here. Yeah, you should have remembered this. So a is a polynomial with mnemonic with coefficients like this going down, a n d minus 1 until a 0. Okay. So and this again, this dg is a common denominator here, and this is a polynomial here. So basically, this is a matrix, a p by m, and this is a scalar. Okay, scalar polynomial. Okay, dg is a scalar polynomial. Okay? Scalar polynomial. So this is a scalar polynomial. Scalar. Okay. 1 by 1. So that's why when you see you have a system with a polynomial, you have a system with a characteristic polynomial. So that's a characteristic polynomial. Think about when m is 1. When m is 1. Okay? When m is 1. Okay, when m is 1. So on this side, okay, it's like Sn plus a n minus 1 s minus n plus a1 s plus a0. So this is my output. Okay. Then this is my input is another polynomial. Okay. So this is my u of s. So then when I do this realization, you will see that the A matrix in the controller norm, we usually write this way, okay? Write this way. So this one is minus A0, A1, until an minus 1. And we usually put n minus 1 in here. So this one is 0. So that's the way we write usually. It's basically you should put dots in here. Okay, you put dots in. So this is I n minus 1. It's the same. You just do this and you get I. Okay. So this one will give us Si minus A is a polynomial like that. Okay. And this polynomial has m of them, so to the power of m. Okay. So in other words, okay. So what if I have this one? So how I should write the A? If you say, let's expand it, then we do, that's probably very difficult. So construct an A that you can still do that. So this is, so you can still write something similar, but you need I2. You need minus A0 I2, A1 I2. So this is like I2. Let me see if I'm right. Yeah, it's still do. This is I2. So this is our I2M. It's the same, okay? There's nothing different. So this is OI2. Yeah, this O 2 by n. Okay. This is M. M is 2. No. This should be like this. So it's a I2 is a 0, 2, 0, 2, 0, 2. That is m minus 1. Okay. No, this is n minus 1. So n minus 1. So then you have something similar here. So this is minus a to minus a is a minus 1 I2. So that's actually gives us a good hint when we have DG. So this is my DG. So this is actually DG SM. That's why they have this. M is number of inputs. Okay. When m is 1, single input, that's our SISO controllable standard form. But you can extend this one when you have multiple inputs, then you have block diagram format like that. So this is just, we don't use the highest, we just use the minimum degree of denomination. So, and again, the B is like that. Output, we have gamma, feed-through term is 0 in this case. So in this case, you have this ABCD realization of a MIMO case. This is a controllable for sure. Controllable for sure. So if you use that method, it may not be observable. Okay, so we'll see observable realization. So here is again strictly proper. P is P output, M input. So state of a realization ABCD state space is Rn. In this case, ND times P, okay, number of outputs is P. Okay, ND is the degree of the characteristic polynomial. So then you can write something very similar to the canonic form. Observable SISO case, observable canonic realization form with the block bag on IP. Okay, so then in the end, your characteristic polynomial is d to the power p. Okay. So again, B is like C transpose, C is like B transpose. Phase term D is 0 because it's strictly proper. So you realize that way is always observable for sure, but it may not be controllable. You're not that lucky. So we're going to go through this example and pay attention to this. Because this is something we commonly see in practice, 2 by 2, 2 input, 2 output. So what is the ABCD corresponding to this? How we can do that such that SI minus A inverse times C, this one. I give you G, which is a 2 by 2. How you come out A, B, C, D, such that SI minus A inverse is B, here is C, A is S. Okay? So that's called realization. So there are infinitely many of such combination of A, B, C, D to do that. But you need to be able to quickly find one. Okay? To follow the step we just showed you. Generalization of SISO's controllable canonic form or observable canonic. So you at least it guarantees controllable if you use controllable canonic form. But observability is not guaranteed. Or you do observable canonic form, but controllability is not guaranteed. But doesn't matter, so because you always will make this one to this one. That's always possible, always correct. But it may not be both controllable and observable. We're going to solve this problem next. It's called minimum realization. Okay? But let's just do one interpretation here. So first of all, can we see this one? Do you see something not proper? So this is not strictly proper. So this relative degree is 0. This relative degree is 1 minus 0 is 1. This relative degree is 2 minus 0 is 2. This relative degree is 2 minus 0 is also 2. So this term gives us trouble because it is not strictly proper. Strictly proper means the denominator degree will be greater than the numerator's degree. So in this case it's not. They are equal. This is the term. Okay. So we can factor out that. So factor out 2, 0, 0, 0 here. So you have 2 in here. So then what do you have is minus 12. Okay, minus 12. And everything here is strictly the problem. So then this term is called D term, directly through term. Okay. So then we set this on G bar, which is strictly proper, and we focus on G bar, and then we'll try to find out derivative first. Okay. Not derivative, it's not determinant. So this guy times this guy minus this guy minus this guy, then you can do that. So then you end up with something called this one. Okay. So this is determinant. So you have something. Determinant is what we want. So it becomes n of s divided by dgs. So this is dgs. So dgs is actually having something like this. Like this. Okay? Like this. And by expansion, you end up with, the reason we put a 0 in here, do you know why? Sorry, the reason we put a divided by 2 here, the reason is to make this polynomial what? Monic. I use this term 10 times. So that this is monic, this is monic. So that's why you need divided by 2. So this is monic, okay, this is monic. And it's third degree here. So that's our dg. So it's not like this is a dg, okay? So this is dg. What is the NFS? NS. So this is so because of the dg, you can write A0, A1, A2, okay? And now we can start to enumerate the coefficients. N of s. So it's g bar s times dg. This is my dg, okay? What is g bar times dg, okay? So I have a dg times this one in. So dg is this one divided by 2 to make this monic. So I multiply this one in, so then I can write something like that. So these are the polynomials. So g11 divided by dg. So now it's a multiply, so you have this n of s divided by 2 still needed. So end up with something like this. Okay, something like this. This is n of s. But we need to write this one in the matrix form, so we're collecting the term. So if for like s squared, we should have -6, 3, 0, 0. For s term, for the s term is -24, 15 divided by 2, half, and 1. So anyway, we can write n of s into, first is s squared, you have -6, 3, and 0, 0. Then you have s coefficient there, then you have constant there. This is my s. So this s is like numerator, it's a matrix form, and denominator is dg, okay? So then, with that, you are so you can express right now. You have confidence that you can write your original g of s. Okay, you write as a d plus g bar of s. Okay, so this is directed through term. So now I'm writing a g bar of s as 1 divided by use a capital D, dg of s. This is a characteristic of polynomial. Okay, characteristic of polynomial. It's a determinant characteristic polynomial. And here you have a matrix transfer function. Okay, of this one, gamma 2 s squared plus. This is gamma 2. This is gamma 2. S squared plus gamma 1, S1 plus gamma 3, gamma 0, okay? Then this dg, actually according to previous, the dg is written as 2s plus 1. Here you have s plus 2 squared divided by 2. So you can expand this one into a polynomial. The polynomial is actually here. Yeah, this one is going to give you s Q plus A2 S plus A1 S plus A0. So those are already giving all these numbers. So given this is a polynomial, scalar polynomial, this is a matrix polynomial, matrix polynomial transfer function. Okay, with that, you use the same SISO controllable or observable canonic form. You will be able to write A, B, C, D immediately in such a way. So you have n of s here, you have 3 coefficients. So controllable realization is boom. It's like this. So basically everything, m is 2. So you have everything is 0. So let me do this. So let's look at the B matrix first. Okay, B matrix is 0, 0, 1. So it's a 0, 0, 2, 0, 2, 1, 2, I2, right? So this is way to learn. And this one is my what? Is a A0. Is a A0, A0, I2. Okay, A0, I2. A0 is a scalar. I2 then is a diagonal. So you can see all is diagonal. So these are coefficients A0, A1, and A2. So then everything is 0, 0, everything is 0 unless this is I2, I2. Okay, I2, I2. And this one we know, this is gamma 1, is gamma 2. No, this is gamma 0, gamma 1, gamma 2. Okay? So gamma 0 this side, gamma 1, gamma 2. Okay? So if you only look at the red one, and think about scalar case, it is exactly the same as the scalar SISO controllable canonic form. But in the MIMO, we can do that as well. And this form guaranteed to be controllable. But it may or may not observable. Okay, we're not sure yet. Okay, not sure. Let's check. Okay, so check the eigenvalues. Surprisingly, you got a -2, -1. So basically, we know. I erase this. So you only have 3, but you got a 6. Remember, polynomial is like s minus. Let me go back. What is the root? Root is s. I want to show you what is the root. Root here is -12. Okay. And -2. And -2. Okay. So this overall system only have 3 eigenvalues. But after the state space, they kind of expanded. It from 3 to 6. So basically, your polynomial is like D, G, M, right? M here is, M is 2, right? So that's why you have multiplicity. Okay? 2, 2. So you have another copy of this one. Okay? So it's not minimum for sure. So this is probably too much a realization is using too much redundant information. Okay? So we have seen this. So the eigenvalues are more than we want. It is controllable using a controllability matrix. So it's, you do this all the way going up to 5 because it's become a 6 by 6 system. Right? So can you go back to see what's this? Is this a 6 by 6 system? Yes. So 6. Also here is 6. Okay. Okay. But remember, original system is 2 by 2. The G. Remember, we started the G of S is what? 2 by 2. Okay. But it's 2 by 2. But DG, we have seen the DG. The determinant of polynomial, the denominator here, is ns divided by dgs. So this dgs is third order, okay? Third order. So, but in the end, the system ended up with 6 by 6, 6 by 2. So this is 6 and 2 inputs. So it become, we wanted to accommodate 2 inputs. We expanded our state, internal state, to 6 instead of 3. By doing that, we already, we still keep controllability property, but we may lose we lose the observability. So we're not going to run through the controllability matrix. It's a fully count rank. So I fully full rank. Okay, full rank. That's not a problem. Okay? But for unobservable part, it is true. But how we can check it? So let's put the lambda is -2 in there. So then we check A minus lambda I and C. So C is this guy. Okay. A is -2. Okay. So then you just add 2 on this diagonal. Okay, diagonal. Then you check this rank. Okay, this rank. Now we don't see it very clearly about linear dependency. You probably need a computer to help you at this point. It is not 6, it's 5. Okay, they lose 1. Okay. So, do you have some ideas you can see? I don't know. It's too hard for me to be. It's difficult. I don't see it very clearly where we have the correlations. I don't see it. Do you guys see it? But you have to use computer to check the rank, okay? I don't see it. So this is a 6 and 8, 8 by 6. So it's not fully rule ranked. Okay. For fully count rank is 6, is full rank. So now it's 5, it's not full rank. Although you have added more rows in here, didn't help, okay? So, how to do minimum realization? Okay, how to do minimum. This is not minimum, but this is a very convenient way to have a realization, and yet it's controllable or observable, but not both. Okay, so it's not bad. It's not bad. I have a way to do it. Otherwise, if you don't have a systematic way, you cannot do it. Even know where to start. So, but better to have minimum realization. So, good news is giving a A, B, C, D as a starting point. You can go to MATLAB to use a minreal to do that, or you do a standard controllable realization. So, this whole system in the end, it should be both controllable and observable. It has to be 3 by 3 system, 3 by 2 like this. Because the highest term in the DGS is 3. So in the end, you come A, B, C, D like this. So it's 3 by 2, 2 by 3. So it's 2 input to output, internal states are 3. 3 is the degree, highest degree of dg. Okay, dg. So let us summarize what we learned today. And it's called MIMO realization, and we can do controllable or observable. It's a directed extension of SISO realization. It's direct. Okay, so it is easy. So it's easy, direct extension. Okay. So next time we're going to walk you through Hanko matrix, Hanko matrices, and also Hanko messages and Hanko matrix. Okay, Hanko matrix. And Markovian parameters. Okay, Markovian parameters. So these are a very interesting concept, and it's linked to our next stage of robust control. I hope I'm going to introduce you next week. Hopefully after the Hanko matrix, we talk about Hanko norm. Hanko norm. Hanko norm. So everybody knows that. The description of the system perhaps is too many variables, too high order, okay? Too high order. So the order too high. Okay? So instead of working on a system model that is too high, can we reduce the order? So that's called model order reduction. Okay? Model order reduction. But when you reduce the order, you don't want to change the property of controllability and observability. You don't want to mess up with that part. Okay? So I want to do a realization. I want to do a balanced realization, both controllable and so we are here. So the roadmap is next. The roadmap is, so we have a MIMO realization. We know it is not minimum. So now how to make it minimum? They said minreal. Okay, I'll help and show you using MATLAB. But this is not end of story. Still, there are infinite many minimum realizations. So then it's called balanced. Okay? Because we have the balanced, meaning the system is both controllable and observable, and both gradients are the same, controllable and. So then, based on that, we have already balanced. Then you can do a Hanko norm based model reduction. Okay, model reduction. So then, this is called balanced model reduction. Okay, balanced model reduction. So that's the right way to go in the future. Okay, when you do model reduction, you cannot say that reduce the order, but you lose many other things. So this is our roadmap. We're going to end up a balanced model reduction. So, and when you do the model reduction, okay. So you have model in G, okay, and you want to do G model reduction, reduced model, and you really hope that this is a reduced model, this is a model. You really need to know what's the distance between them. So it's called error bound. Okay? And interestingly, the error bound of the Hankenon-based balanced model reduction is exactly the known as very tight. Okay? It's very beautiful. You got to learn next week. But it's part of the robust control, but I'll add a little bit next week. So stay tuned next week about model reduction. Let me now go through minreal with you. So here is something we can show you in MATLAB. So in MATLAB, there are some surviving things. Say for example, I want to find out something realization. I don't know what is the command. Okay, what you should do. There's a Google command. It's called look for. Can you see my typing? Okay. Have you used look for before? You haven't. I know you haven't. So look for realization. So you see what's going to happen. So look for realization give you all this type of realization. There's a command with all the realization, container realization in there. So that's funny. So you can see they also using a balanced realization, minimum realization, I understand. Okay. So this is something minreal is called minimum realization, post-zero cancellation. So you know that you have a say for example, let me give you a trick, okay? So I mean in computer, okay? So you say that, oh, use a transfer function, you got a numerator, you got denominator, right? So this one will give you a LTI object. So you have G of S, right? So it's A of S, B of S. But you see here you have A bar of S. This is S minus S plus A, B bar of S, S plus B, S plus A. So you have a common factor. You want to remove it. So you end up with is actually you end up with a G bar of S. But G bar of S, in math sense, these are the same, okay? Are the same. But in MATLAB, they are not. You have a bigger polynomial, but that factor you don't know, you didn't eliminate it. I want to squeeze that one out, do this cancellation, what we are going to do. Okay, so using minreal. Okay, let's click the minreal. We're going to right click it. We haven't really learned minreal yet. We're going to learn next. This week we only did a very direct realization of controllable canonic form, mimic the SISO case. So here they give a hint, they say, oh, it's not minimum, I want something minimum. Both controllable and observable. So use this one, okay? So SIS is meaning, you guys know what SIS? SIS is an LTI object. LTI object. So when you, like SIS is LTI object. And this SIS could be SISO, could be MIMO, could be continuous time, could be discrete time, could be with delay. Okay? That kind of thing. Okay? The LTI model SIS, the current model MSIS is after the minimum realization. They will make this post-zero pairs removed, or non-minimum state dynamics eliminated. Okay? For state space model, minreal produces a minimum realization of the min SIS of original SIS. Original SIS may not be minimum realization. So the all uncontrollable, unobservable modes all removed. Okay, so that's minreal SIS. Okay, you can add the tolerance for the post-zero cancellation dynamics. So this usually tolerance is EPS. EPS is external. It's an internal. Let's say what's the EPS? Oh, EPS. EPS is it's called epsilon. Okay, epsilon. It's a machine accuracy. Okay, machine accuracy. So this is if this guy is A and this A difference. Sometimes they have some not exactly the same. So numerically, this difference is less than this epsilon, then they are the same, they cancel out. But you can say, oh, if they just plus or minus how many percent, you just cancel them. Yeah, you can do that. You can specify what kind of tolerance you want. Okay. So if you have A, B, C, D, what you should do to make it LTI object, you just put A, B, C, D, SS, will turn to the SIS, okay? To the SIS. To the SIS. So when you do the minreal, okay, when you do the minreal, they will return you a similarity transformation U. It's an orthogonal matrix U, such that orthogonal meaning its transpose is the inverse, okay? So if you have a U matrix, okay, its transpose is U inverse, or U transpose is I, okay? So this is orthogonal. So that's why you can just do U prime, U and C U prime will get you so the Kalman decomposition of ABC. See, MATLAB wise it's very easy to do, but you really need to know what's really happening behind the screen. Okay, that's I wish you are going to play with this thing, and there's a documentation for that. So this is minreal. This is interesting. Okay, let's see an example here. So ZPK means what? Zero pole gain. Okay. So this is also so to generate LTI object, you have multiple ways to do. One is TF, one is SS, one is ZPK. So these are different forms of the functions. So in the ZPK case, your transfer function of 2s per 1 is h. So inverse of 1 plus gh. Okay, 1 plus gh. Okay, and g. So this is a closed loop. This is a closed loop. Okay. So basically, it's like you have a g, you have h. G is in here, h is in here, and so this is g divided by 1 plus gh. Okay. 1 plus gh. Okay. And this is a SISO system. So G is ZPK. And so H. So ZPK, you have S plus 1 and S minus. So this G is what? S minus 1, S minus 1. Okay? So pole is 1, 0 is 1. Okay? then this is 2s plus 1 and divided by s. 2s plus 1 divided by s. Then just close the loop, then this will give you this, and inverse it. So, in the end, you come up with a closed loop transforming like this. You can see there's a cancellation. So, I really want to remove this s minus 1. Okay? So, what do? You just say minreal C loop. C loop is LTI object. Okay, LTI object. So then you will C loop minimum. Then after you've done the C loop, you cancel out that. So sometimes this is like you know it. Okay, you know it. Sometimes you do not know it. Okay, do not know it. So you just do a transfer function of this one. You try to simulate it. You'll get an error. You'll get an error. So it's better to have a habit. You have a system, then do minreal, you're gonna go to minimum system, okay? After post-zero cancellation. So there's an app called model reducer. This is a kind of model order reduction. So this is second order. The original system is third order. This is a third order, okay? Like balanced model reduction and model reduction. This is post-zero simplification model reduction basics. So if you are interested, you can read something on the model reduction basics. Okay? So there are lots of ways to get a reduced model, and in practice, it's very important to get a reduced model. But how you can guarantee it's still controllable? And there are many different ways to. So they tell you the approaches, and the commands, and how to do approximation. I think the most important thing is this one, okay, called balanced realization. So basically, the reduction is based on the importance of the states. Then you remove those on the bottom, so it's the least important ones. So I'll show you examples next week about balanced reduction. Of course, when you are a control person and you don't use MATLAB, it's hard to imagine. In fact, MATLAB was invented by the guy in the control area. So in fact, everything behind MathWorks is the driving force is usually the control terminology. Okay? Plus linear algebra, numeric linear algebra. So whenever you see some commands and you just dig it deeper, my job here is to make you understand what's going on behind some math foundations. So I only went through MIMO realization by canonic form, direct extension from SISO. To be frank, there are infinite many ways to do MIMO realization. You can write a paper to name that realization under your name, okay? But only if many people believe, oh, this is the way to go. So there are methods using very different types of realization. But with computer today, with balanced realization already, those existing named realization is not important. Okay, don't read like I know there's a Gilbert realization. I read it, so it's not impressed. So, okay. So follow my way, know the basics, and learn how to use MATLAB tools. Okay. See you Monday, and have a productive weekend. Don't do to people and very dense population. There was emergence